Hey folks, happy Tuesday. Doing well? Alrighty. Just had a little blip there with the network, but I think it's going okay now. I'm back to regular. So let me know if it's real laggy or not. I think we'll be okay. We'll look and see. Try and keep an eye on that. We got a couple things to talk about today. We're going to get into priority queues. First, we'll talk about the lab. The last little bit of lab we did on trees, doing the breadth first traversal. So this one I asked you to do the traversal on to see, can we take a tree and navigate, and specifically the breadth first, where it goes each level at a time. So first level the root, and then the next generation, and does all of those in that generation, and then it goes down to do all the ones in the next generation. Right, on and on and on and on. So the textbook had some pseudocode example, and kind of how we could follow along with that. So we're going to try and do that one first, and we'll move on to priority queues. This actually picks up the last little bit of the trees section as well. We didn't get into storing a tree with an array or a list, and that's what priority queue is actually going to take advantage of. And we'll take a look at that in a little bit. So we've got today, and we've got Thursday to talk about priority queues. I did get all the midterms graded. Didn't go as well as I was hoping. I'm not entirely sure why, but you know, it's a crazy semester. I think our average was only 75%, and given your practice midterm was the exact midterm you got, I was a little surprised that scores were as low as they were. So, you know, it's okay. We can recover. It's not the worst thing in the world, and it's not a huge portion of the overall grade, but some big misses on some of the questions, for sure. I don't think I've got a question by question analysis. I can see. Maybe I do. Maybe I can see if I can find that. I think I might even have a question by question. Let me see. There's some tool I can look at. Let me see. Might be worth talking about for a minute, and we'll see how it goes. Let's see. Is it quiz statistics? That might be it. Let's see. It's loading. It's loading real slow. Just thinking hard about it. Okay, yeah. Okay, so I got some statistics in there. We can do that. Take a peek at these. Oh, okay, the average was 80. I thought it was 75. I think I was maybe misspoke there. Okay. You want 100% on the first question. That was pretty good. The position wrapper with the linked list. Right, the idea with this one is once you have the position, there's no traversal. Right, because the position knows where it is. You don't have to traverse the linked list to get to a given position there. And once you have a position with a linked list, you just change the links. There's no n operations that has to happen to do any shifting. That was pretty quick. Pizza went mostly well. A couple folks had some trouble with it. But overall, that went pretty well. The unit tests were a little hit or miss. I was expecting us to be better at unit tests by this point. Uh-oh, it says my bitrate's bad. I think I'm still there. Unit test, asking about that was great. This one here, I was a little surprised on. Remember, to remove an item by index in a linked list, you have to get to that index. So this is an n operation, or k, whatever the index is. It takes k operations, up to the size of index to get to it. So if you're removing the last thing, right, well, it's still going to take that many operations, right? If we have an index in a dynamic or an array-based list, we can get to it immediately, but then when we remove it, we still shift. So removes are still slow. That's what that position wrapper is all about. If we have a position that we're locked into, that happens real quick. Our sum here went relatively well for some people. Again, this was having to deal with the indexes themselves. So we had to loop using the range and the length, or I think a person or two used enumerate, so you get out the value and the index. Worked out well. This idea here with the abstraction encapsulation, we hide away all of our private details and we expose the public functions, right? The recursive function did not go well at all. A couple people did good at it, and then a lot of misses here with this recursive function, right? And in this case, all this recursive function was doing was serving as a loop. So we just had to chunk it down one letter at a time, right, until we got to our base case of there's no letters left, or there's one letter left, whichever way you wanted to write your base case, and return those ordinal values. You guys are great describing the process of finding a solution. That's good. The iterative solution, which went much better. This is just the loop without recursion. We just loop through every character, turn it into an ordinal, and add it. Inheritance, that was good. This making a copy was happy with this answer. Everyone got the many base cases. And this last question here, the average time it takes to look up an item by value. Remember, if you're looking up by value, you have to go look at every single item until you find a match. So K or N numbers, right? And it might not even be in the list. So like the worst cases is not in the list. We looked at all N items. So our average time here is N, O of N. Okay, so we got that one all graded. Hopefully that's all out there for you folks. Let me know if you have any questions about it. I think you can see your questions in your score. If you can't see that, let me know. I can adjust as needed, of course. But if I set that up wrong there. Oh, and I think this was a second window, so have this one open, right? All right. So we're going to talk about the lab first. Let me open up our trees here. Our N tree is the one I asked you to do the breadth first traversal on. Right? So I'm just going to make sure I'm doing this the right way here. And go grab our example, our pseudocode here from the text. Right? Used a queue. The idea was we visit the item and then we queue all of its children. And what we do is as we visit them, we return that item and we queue all of its children. So that way we're getting these generations at a time. So if we open up the whiteboard here and take a look, let me actually sit up a little bit here. Is anybody around in chat? You guys all fall asleep? Okay, the idea here is if we have some sort of N tree and it's got a bunch of children here. Hey, how's it going? You know, sure. Those have children. Maybe this one has a bunch of children. Who knows? This one might have a child. That one has a child. This one might have two more. Right, the idea is we get each generation at a time. Sorry, some of those are a little overlapping here, like that. And then these last ones here. That's the breadth first traversal. All right, I guess no questions is good, right? Yeah, if you have specific questions, feel free to chat with me after. You can take a look at hydration. Thank you so much. Appreciate it. It's coffee time. I have to go make my next pot of coffee. It's gonna be a long night, but I did get my new mug. I'm super excited. So I can represent the OG chess streamers here. All right. They told me they're not going to give me an affiliate link though, so I can't make money referring people to buy their merch, which is real sad. Always looking to make money for that scholarship fund. Ooh, I should tell you, because this is cool, right? Why not? We had the Giving Blue Day for U of M's big fundraising push day. And I will show you here. Because why not, right? I can show you all these things. Let's see. See if I can find it here. So this so far, no payouts. Ooh, sad in Twitch. But you know, we're getting close there. I think it has to hit 100 before it'll go. So we're at 18 something or other. I think they go more than 30 days. Like, I forget. There's a way to do it. To see all the revenue here we're making for the scholarship fund. So let's see. Yeah, here we go. Here we go. Donation to the scholarship fund. Where is it? Where is it here? $50 out to the scholarship fund for CECS. Thank you. Twitch hasn't paid out yet, but I think I hit about $50, so I wanted to throw that out there. All right. So we are cruising along with that. Thank you for your support. All right. Anyway, so the breadth first traversal, right? We wanted to go and visit the level and queue its children, and we're going to keep doing this as long as the queue is not empty, is the idea, right? So we want to just open this up here, make sure I've got the right stuff. Turns out it works out better if you try and not do this from memory. Did you realize that? Trying to do all this stuff from memory does not work out as well. And this is what we would end up with a repeat of last week, which was no fun, that Tuesday. So we're going to do better, right? I will follow the text because it works, right? Go figure. Do you guys actually read the textbook? Curious here. Let me throw out a poll here. Wondering if that's helpful or not. Do a new poll. Read the textbook. Yes, a lot. Yes, a little. Oh, let's just do a lot. A lot, a little, or none. Okay. Just curious. You can respond to the poll there if you want. All right. Well, yeah, you can just chat it. Thanks, Sammy. That's good. Yeah, for sure. It's a good resource there. I try and give you the highlights, but definitely a good resource. All right, so for our N tree then, when we do our traversal, right, this idea that we want to start traversing items. We had these like this subtree pre-order, we had the in order. Didn't I have the in order in here? All right, so let's add that here. So we're going to define a breadth first of self. So we need to make a queue. So first we create a queue here. Let's see. All right, so a couple people read the textbook a little. One person reads it a lot, and nobody doesn't read it. That's good. It's good to know. Okay, so we're going to make our queue first. And we could use a queue class, or we could just use the list for now. This is not a big... we don't have a lot of items in here, so we know this is a bad queue, but it's okay for now. So we'll just make a list. So we'll say our queue is a list here, and then we're going to add the root item to the queue. So queue append, remember first in, last out. So we're going to append to the end, and we're going to take from the front. Right? So we're going to append self.root. Okay? Then what we need to do is we're going to take this queue and we're going to keep on looping as long as it's not empty. So while the length of my queue does not equal 0, we can do something. So we start with root, and as long as we don't have 0 items, we're going to keep on going. Okay? So what we do is we're going to yield that position, q.dq. Actually, no, we need to keep that position, sorry. So the position, or current position, is going to be our queue, and we can't dequeue anything, right? So we want to pop off index 0. That's the front, right? Add implementation of dequeue. I just don't want to have to go copy paste. That's not, I mean, we've talked about queues. We understand what a good queue should do. We're doing a bad thing right here, and we're going to feel bad about it, but it's okay. Okay. A list literal. What does it want to do? Oh, okay. Yeah, sure, with self-root. Sure. Save one line here. Queue starts off with root. I like it. We got the current position. And then what we're going to do is we're going to yield that position. Then what we do next, right, the next thing that happens, we're going to say for child in self.children, right, of the position, we're going to q.append the child. Okay? So we're going to yield the position, and then for every child that we have, we're going to put them in the queue. When they ask for the next one, we're going to check if the length is not 0, go get the first thing. Right? So if we just throw some numbers in here, right? Let's do maybe a slightly smaller one. So we'll have maybe like 10 in here, and then we'll have, I don't know, 25 and 7, and maybe 20 has a 3 and a 2, and 5 has a 9, and 7 might have no, I don't know, maybe 7 has a 50. So the first thing we're going to do, right, we got this little queue over here, we're going to put 10 in. And then we're going to pop 10 out, we're going to give them 10, and then we're going to add all the children. We're going to put in 20, we're going to put in 5, and we're going to put in 7. Remember, and these are position wrappers. So then the next thing that happens is we're going to spit out the 20, and then we're going to add all of the children of 20. We're going to add 3 and 2 to the queue. And then we're at 5. We spit out 5, and we add 5's children. We add 9 to the queue. Then we go to 7. We spit out 7. We add 7's children to the queue. We add 50 to the queue. And then we go to the children's children. So the next thing in the queue then becomes the 3. The 3 has no children, so it doesn't add any. Then we pop out the 2, we pop out the 9, we pop out the 50. So it's a breadth first traversal going level by level by level. Let's see if we can do that. So I think we can do that. We'll say for position in root.breadth first. We have to just print the position.data. We'll see if we can run that. Here, let me maybe comment out some of these other prints here for now. Okay. Oops, that's right. I can't. I need to also count out the for loops. Sorry. All right. Ooh, position is not defined. Where? Oh, it's current position. Sorry, current position. Children of current position. Okay, that's right. That's why it was gray there. We hadn't run those. Okay, so the breadth first traversal. Maybe we should print that out. So this is a print. Breadth first traversal. That's level by level. Okay. So we see here's the top level, and here's all of the direct children, right? Lab 1, Project 1, and Hello World. Those were all added right to our root. And then we get the next level. So inside of Lab 1, right, we added a Lab 1 PY file. Inside of Maze, Project 1, we added a maze solver, we added the main, we added the unit test, and that was it. Does this part make sense so far? So this breadth first traversal, let me zoom in a little bit, sorry. Right, so we're taking advantage of a queue. I know this is a bad queue, I'm sorry. I'm feeling really bad about it, but I didn't want to go copy paste some other code. Okay. This means we have to do lots of shifting, so yeah, that's bad. Right, questions about what we did here for the lab then? Breadth first, did I typo it? What does it want to do? Rename to... It's not bread, is it? Is it bread? Bread, TH? Breadth? Yeah, that's right. I don't know why it thinks it's a typo. I don't know. That's okay. We'll live with that. All right, so let me commit that to GitHub here. So that was lab, what was the number for that one? I don't remember. I think that was 6, right? Because all of you were doing 5 yesterday, because everyone seems to be a week behind, which is unfortunate, but that's what it is. Sure. This is 2001. Here we go. This is lab 6. Okay, maybe we would want to check, like, if we're not empty, do something first, because otherwise, if we're empty, root's not going to work. But like, we can't really make an empty tree right now, so we haven't gotten that far. Okay. How are we feeling so far? You know, trees are a whole other way of thinking. Once we get to this this idea of being hierarchical instead of order-based. Very different. So 8.3.2 is all about the tree in a list form. Now, actually, that's what we're going to take advantage of here. It's an array-based representation, and usually of a binary tree, because that makes it easiest. So the idea here is actually really cool. So let me pull up the whiteboard here, and we'll make another one. Okay. So imagine we had a tree here, and just use your imagination, right? So we have, I don't know, 7, and then this one has 2 children. It's a binary tree with a left and a right, and maybe, I don't know, a 9 and a 12 and 20, and this has, I don't know, 31, and this one might have a 55. Sure, just some numbers, right? So the idea is we can store these values instead of having to do links with the linked node, where you have the link to the parent and the parent has the links to the children. We can put all of this information into a single list of size, and this is the fun math here. It's size height, 2 to the height. Right? I think it's size 2 to the height. So the height of our tree here, if it's just here, is 0. This is height 1, this is height 2, this is height 3. Is that right? So 2 to the 0 gives me room for 1 item. 2 to the 1, no, it's got to be plus 1, sorry. I think plus 1. Let's try that. So I would get room for 2 items, or I can store the 1. With 3 items here, then I'm 2 to the 2. I have room for 4 items. With the next generation, I'll be 2 to the 3. And if I were to have all the children here, right, you know, we might have something here, might have something here. We have 1 item plus 2 items plus 4 items plus 8 items plus 16 items, right? So the max number of spots per level here, right? If we look at that, then this is items. So this is, I don't know, or items here. And then if we want total items, right, the sum here is still 1, but then it's 3, and then 7, and then 15, right? And then 31. If we add all those up, right, it's the next height. So it's 2 to the power minus 1 is how many total items we have. So we can store a tree of height something in a list of size 2 to the height plus 1. Right, so if my height is 3, I have 2 to the 4th. So 2 to the 4th, 2, 4, 8, 16. I'm going to have 16 indexes here, right? On through. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Okay, 16. And what we do is we put items in order, like by level. So 7 goes here, and then 9 and 12, its children, and then 9's children, 20, and then a blank space there, 31, another blank space there, and then 20 has no children, so blank for 20's children, and then 20's children, or 20's sibling here, this blank doesn't have any children, so 2 more blanks. 31 doesn't have a left child, but 31 has a right child, so we put the 55 in here, right? And then this blank here doesn't have any children, so 2 more dots. All right, so sure, that minus 1. We'll do 2 to the height minus 1 after the fact. So 2 to the height plus 1 minus 1 size. We can store it. Okay? So what you can do is if you know your index number, right? Because one of the things we did, we said, hey, given this position, give me the parent, or give me the left child or the right child. Right? To do that, it's just arithmetic now, which is really cool. So what you can do is you can say, hey, your parent's index, right? So the index of your parent is u divided by 2, because this is index 0, 1, and 2, and it's so your parents, it's rounded up minus 1. So your index, right? You're either index 1 or 2. You divide by 2, you round up, and then you subtract 1. So you're either going to get a 1 divided by 2 rounded up, like the ceiling of that. I think that's our math notation for ceiling, right? Minus 1, or we're going to get 2 divided by 2, ceiling of that, minus 1, right, will give us index 0. That's our parent. Okay, so we've got some arithmetic we can do to find our values. Okay, to find the left child, right, to find the left child, we're going to multiply ourselves times 2. So let me need a little bit more room here. So let's do this. Let's table all this out here. So we have index here, and then we have parent, then we have left child and right child. Oh, that's right behind my webcam, isn't it? Okay, so index, parent, left child, right child. So parent is divide by 2, rounded up, minus 1. Your left child is times 2 plus 1, and your right child is times 2 plus 2. Okay, so at index 0, we have no parent, right? It's invalid to be negative 1. That's obviously no good. But at left child, 0 times 2 plus 1 is 1. 0 times 2 plus 2 is 2. Works out so far. Index 1, its parent, divided by 2 rounded up, is 1, minus 1 is 0. Its left child, well, 1 times 2 is 2, plus 1 is 3. Its right child is times 2 plus 2 is 4. Okay, index 2 here, right? So this was index 0 was the 7, index 1 was the 9, index 2 is the 12. So at index 2, our parent is divided by 2 rounded up, minus 1, 0. 2 times 2 plus 1 is 5. 2 times 2 plus 2 is 6. Okay, so let's see if that checks out. So now index 3 then, right, so index 3 would be the left child of 9. Right, we're at 0, 1, 2, 3, 4, 5, 6. Right? So 3, ceiling divided by 2, right, is 2, minus 1 is 1. Right? Its left child times 2 plus 1 is 7, times 2 plus 2 is 8. Let's check out index 4. 4 divided by 2, ceiling, 2 minus 1, 1. 4 times 2 plus 1 is 9. 4 times 2 plus 2 is 10. So at index 3 here then, right, we had the 9. I'm sorry, nope, I can't count. Index 3 is 9's child, sorry, is 20. That was 20 here, index 3. So its parent is 1, right? Its children then are going to be index 7 and 8. 9 and 10, 11, 12, 13, 14. Did that check out? Is this at index 12 over here? So we're at 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Index 12. 13, 14. Looking good so far. Okay, so if we keep on going, index 5. Now, so index 5, we would expect its parent to be node 2 here, right? That's the 31. Here, that's index 5. Okay, its parent should be 2. And 2 is at index 2. So 5 divided by 2, rounded up, right? We get 3 minus 1 is 2. Looking good so far. So its right child, 10 plus 1 is 11. Its left child 11, right child 12. Now 6, right? 6 is the other child of 12 that we don't have. That's over here. It's empty, but it would be. So its parent, 6 divided by 2, rounded up. 3 minus 1 is 2. Child here, right? Left child times 2 plus 1, 13. Right child times 2 plus 2, 14. Okay, so you see, it's just some simple arithmetic to get positions out. Now, I know that looks crazy here, but it works out well, but the downside is, right, there's no guarantee, because pretend we hadn't talked about, even with the binary search tree, there's no guarantee. Our tree could look like this: 10, 11, 12, 13, 14, 15, on and on and on. This is a tree, right? We just have no left children ever, right? That's okay. That's still a tree. So we could get into a really bad form because we're to the height, right? 2 to the height. So the amount of size and storage we're going to take up is kind of prohibitive to use an array-based tree usually. Okay, but what we're going to do is we're going to use that here in a second. We're going to use that idea with a new data structure. This is priority queue. Now, a priority queue is a really cool data structure. I'm a big fan of priority queues. You are very familiar with queues, right? The line at the grocery store, right? Line at the grocery store, you get in line, first come, first serve, right? Next available register you go to. Okay, that's a regular queue. A priority queue, you could imagine like the emergency room, right? You go to the ER, you've got a cough, someone else comes in after you and they've got a head injury because they fell and bumped their head. They're going in first, right? They have a higher priority. So what the priority queue does is it says the top thing should be the highest priority. And we can either have min queues or max queues, whatever you want to define. Either it's the smallest value or the largest value. Either way you want to define it, perfectly fine. Right? We can do either. It's not a big deal. Okay, totally up to your definition there. But that's what the idea is. So, and typically what we do with priority queues is we will do this in a key value pair style. Right? It's kind of like a dictionary where you have a key and an associated value. So our class for priority queue, oh, that's tiny here. Let's enhance a little. Class for priority queue, then, right? It's going to have an init method here where it's going to store a bunch of things, right? So we have self.data is a list, and that is private here. Okay. And we're probably going to size it off, put one thing in there to start. Right, that's okay. And then we're going to have define an add method that takes a key and a value. And we're going to assume the value is none unless you tell me otherwise. And what this cool trick does is if you only want to add keys, great. We never have to associate values. Right? You don't need to use the key and associated value. You can just add a key, and we're going to use our priority queue just fine for the key. If you want to add a value, great. We can do it. But if not, that's no big deal. Right? So some stuff has to happen here. For now, I'm just going to hit pass because we're just kind of defining some methods here. We're going to have a define remove min here. So we're going to say this is a min queue. So we're going to keep the minimum there at the top. And we're going to have a min here where we just show you what the minimum is. So this one's easy. This one is we're going to return self.data at 0. Okay. We're just going to give you the first thing. Right, that's because the first thing is always going to be at the top. And we'll look at that in a little bit here. We can give you the length of our priority queue. So we need to be tracking a number of items, self.number of items here. Because remember, the list is going to be oversized. We're not guaranteed to have items inside of our queue if we're oversized with this list here. Because we use that array-based storage where it's always 2 to the power of number of items. So I'm going to return self.number of items. Self.number of items. Come on, type ahead. Okay. Length, and then we'll also have an isEmpty method here. So for empty, we're going to return self.number of items. Why doesn't it find number of items? That is weird. Equals 0. If we have 0 items, where empty is true. Oh, I never finished defining it. That's why. Yeah, start off at 0. Right, so adding here, obviously, is going to take our number of items plus 1. Okay, we're going to add here. Now, what's cool with the priority queue is that we can allow for duplicates. Right, usually with like a dictionary, we don't allow duplicates because that's a set. So a priority queue is not required to be a set. You can have duplicate values here. But what happens is that we have some fun rules with a priority queue. Right? The idea with a priority queue is we're going to store our values in a array-based list, or I'm sorry, an array-based storage area. So we're going to use a list to store our items, and they're stored in a binary tree. So we're going to use a tree structure that's stored in an array. We're going to use tree structure, binary tree structure. in array-based storage. Okay, because we can always get out particular values here. Okay, so what we're going to do is we're going to have an item. So we're going to have a class here for item, right? And we could even mark this as a private class here for fun. This is going to be private item. So we can define an init that takes a key and a value. Right, so self dot, I should name those better, sorry. Key and value. Self dot key is the key, and self dot value is the value. Okay? And then we're going to define a less than operator here. We're going to return self dot key is less than other dot key. So if we are less than, we get true here. Okay? That's all we need so far. So we're just going to be able to compare less than because we're a min q. So we only need less than because we're a min q. That means we keep the minimum on the top. Okay? So is empty? Great, easy. If we have no items. Oh, here, we can even say, length, that's fine. Length of self equals 0. Look at that, isn't that cute? Okay? Now, the book will go through and give you some other implementations, and they'll talk about why they're bad. I'm going to skip the bad implementations. Okay? It's not worth our time to see why these are bad here. Right? We can talk about it, but we're not going to write it. So imagine then we had a priority queue. Sure, let's imagine that. Where we just put everything in a list. Here. So you throw a bunch of values at me. Right? I don't know, like 10, 20, 7, 5, 42, 15. I'm going to give you the smallest one out. So adding things is super fast. Right? Adding to a list, constant time, on average. Right? We've talked about this amortized average here. Getting the minimum item, though, means I have to go look. Are you the smallest? 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 And I have to look at every item to find which one was the smallest. Remember, like you start with smallest. Small is this one, and if you find a smaller one, small now becomes that one, small becomes that one. So then I can give that one. And then the other ones have to shift down. So we have to look at n items, and then we have to do n shifts. Right? It's terrible, terribly slow. Okay, that's an unsorted list. Now we could implement it with a sorted list if we wanted. So say we were to create a sorted list. So okay, so let's add 10, let's add 20. Then we go to add 7. It says, oh, 7 is the smallest. Bump 20 down, bump 10 down, put 7 in the front. Okay, add 5. Bump 20 down again, bump 10 down again, bump 7 down again, add 5. Right? Okay, 42. Well, it's bigger, 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 bigger. 42 goes at the end. Okay, still n operations to add something. Now what's cool though, right? To get the minimum item out, right? And actually we would probably do this in reverse order, where you'd keep the biggest at the front, right? 42, 20, 10, 7, and 5. And then to get the smallest item out, you just give them the last thing, right? To remove that, you just give them the last thing and remove it, pop it off. So adding is slow. So in a sorted, add DD is slow. In the unsorted list, sorry, where'd they go? Oh, and in the unsorted list, unsorted, remove is slow. Right? Those are terrible. Right? And we can see now that it's not going to work because that's too slow. Right? We can do better. So what we're going to do is we're going to use the heap structure. So we call this a heap structure. That's our binary tree in a heap structure, right? Or a binary heap. Okay? So what we get is we get some really good performance out of it, because what we are going to do is we're going to have this heap order property. We're going to say we're going to guarantee that our heap will be in a particular order, that for every position, right? So if we had a bunch of values in here, so we had 10, we had 20, we had 30, we're going to say for every value it is greater than or equal to its parent. So it has to be greater than or equal to the parent. Greater than or equal to the parent for every value. So here we can't put an item that's smaller than 30 in. We can't put a 27. That would violate our heap order property. So that's no good. Okay? But we're going to maintain this order here when we create our heap and structure our heap. And what we're going to do when we keep our tree structure, is that we're going to start filling things level by level by level here from the left. So we're going to maximize every position here. So what that's going to do is, remember back to that array-based storage, right? It's going to mean there's no gaps. So if we don't have 7 items, we're going to take off this child here. If we don't have 6 items, we're going to take off this child here. Maybe we'll just have 5 items. So we're going to fill from the left. What this means is we are, we'll call it a complete tree. That's a way of terming trees here. All right, so give me just a second. Oh, I lost my video here. Let me throw on some music. We'll take a quick 5 minutes, and then we'll pick this back up with some more tree terminology. All right, be right back. Hey, folks. All right. Does not look like the connection here is very stable. That's crazy. It's been all over the place while it's on break. Is it really laggy? I think it's really laggy. Let's see. Like, it says I've got 2,000 kilobits, but then it's like, it goes back to red. I don't know what the deal is. It's been stable all up until now, I think. And I keep losing you folks. Let's see if I can pick it back up. Okay. All right, we'll just plan to finish up on Thursday then. No need to suffer through this. All right, and I think we got far enough that we'll call it good for now, okay? So sorry for the trouble. Yeah, it might be Twitch. I don't know if it's... I was having trouble trying to do some other stuff on the internet too, so maybe it's my connection. Oh, now it says it's stable again. Are we back? How's it now? I just had to threaten it, right? Maybe. Ran out of coffee, so I had to switch to Coke Zero. Definitely not as good. Oh, no, okay. So it's no good. Let's call it a day. We'll be back up Thursday, okay? Sorry for the trouble. It's definitely not stable enough. And we'll go from there, okay? So you folks take care. I'll see you on Thursday. We'll finish up our priority queues.